Work energy theorem. Consider a block with mass m moving along a horizontal surface which is frictionless under the actions of a constant net force F net. So as it moves to the right, it will undergo a displacement S. So class, according to the Newton's second law, we understood that when there is a constant net force, means the object will experience accelerations. So we are going to have summation force equal to F net equal to ma. So as the object undergoes a displacement S, its velocity will change from initial value u to a final value of v. So by using the equations of linear motions, providing that the initial velocity is u, the final velocity is v, then we are going to have v squared is u squared plus 2as. So I rearrange the equations. The acceleration will be v squared minus u squared over 2s. So I put this as equation 2. So I substitute equation 2 into equation 1. Then I'm going to have F net equal to m v squared minus u squared over 2s. Then I move the displacement s to the left hand side of the equations. Then I'm going to have F net multiplied s will be half mv squared minus half mu squared. So recall the concept of kinetic energy. So the half mv squared will actually refer to the final kinetic energy of the object. Half mu squared will referring to the initial kinetic energy of the object. And so K final minus K initial actually is referred to the change of kinetic energy, and the F net multiplied displacement actually is referred to the total work done. So we have W equal to delta K, and this is what we call work energy theorem. So according to work energy theorem, the work done by the net force or the resultant force on a body is always equal to the change in the body's kinetic energy. W is delta K. So the delta K is K final minus K initial. So the K final can relate with the final speed. So we have half mv squared, and the K initial, the initial kinetic energy can refer to the can relate with the initial velocity. So we have half mu squared. So again, I remind you, the W here is referred to the total work or the net work done in the system. So work can be positive. When our work is positive, it will telling us that the kinetic energy is increases, whereby the K final is greater than initial K. So the particle is going faster at the end of the displacement. Then our W might also be negative. So in this case, we will find out that our kinetic energy is decreases, whereby our K final is less than K initial. So it means that the speed is less after the displacement. Means the object actually is slowed down. Okay. Then we might also have work W equal to 0. So what is implied by the W equal to 0? So the W equal to 0 will telling us that our kinetic energy is stay the same. The K initial and the K final is the same. So it means that the speed of the object doesn't change along the displacement. Okay. So be careful when we apply work energy theorem. We have to bear in mind the work done by the net. The work done here is still with the work done by the resultant force. It shouldn't be just applied to one of the individual forces that act on that particular system. So class, let us see one example how we are going to apply the work energy theorem. So let's say I have a 6 kg block initially at rest. I pull to the right along the horizontal frictionless surface by a constant force F of 12 Newton. Okay, so I want to find the speed of the block after it have moved 3 meters. So I want to find what is the speed of the block after it moved 3 meters. So class, for this particular block, beside the force 12 Newton, Actually, there will be normal force acting on the block because the block is placed on a surface, and then because the block has mass, there will be weight acting downwards. So initially, the velocity of the block is 0 because very starting it is at rest, initially at rest. So I'm going to find what is the speed of the block after it moved 3 meters. So how I'm going to calculate the speed, the final speed of the block? We are going to apply work energy theorem. So applying the work energy theorem, the total work done or the net work done will be equal to the change of kinetic energy. So the change of kinetic energy is referred to the final kinetic energy minus the initial kinetic energy. So the total work done here will be the work done by the normal force plus with the work done by the weight plus with the work done by the force, then equal to the final kinetic energy can relate with the final speed that we want to calculate, which is half mv squared, and the initial kinetic energy can relate with the initial velocity, which is half mu squared. So if we refer to the figure given, you will find out that the normal force and the weight is perpendicular to the displacement. So when it perpendicular to the displacement means the angle between normal force and weight with the vector displacement s is 90 degrees. So any forces that perpendicular to the displacement, the work done will be 0. So there will be only work done by the force 12 Newton. Then if you refer to the figure, the direction of force 12 Newton and the directions of displacement is both rightward. So means that the angle between the force F and displacement S is 0, 0. So I'm going to have the work done by normal force is 0. The work done by the weight is 0. So the work done by the force F will be the magnitude of the force 12 multiplied with the displacement 3 meter, and the angle between the force and the displacement is 0. Then on the right hand side, I'm going to substitute the mass of the object 6. Then v is the final speed I want to calculate. The initial speed of the object is 0, so this one will become 0. Then do the calculation, I will get the final speed of the object after 3 meter is 3.46 meter per second. So you might try to attempt tutorial for questions 6, 13, 14 and 15 by using work energy theorem that we discussed in this video.